Hey everyone, and welcome to the section of advanced problems in Prolog. On this lesson, we are going to solve the problem 12. This problem 12 states, consider two groups of 10 people each. The first group, the percentage of people with Parkinson among smokers is higher than among non-smokers. In the second group, the same is the case. But if we consider the 20 people of the two groups together, then the situation is the opposite. The proportion of people with Parkinson is higher among non-smokers than among smokers. So can this be true? Write a little Prolog program to find it out. So given this statement, I want you all to think if this is a real possibility, right? We have a trend that appears in two groups. It can also be more than two groups, right? We have here a set of groups. This trend is followed in each of these groups. However, when we combine these two groups in this case, then the trend is the opposite. What is happening here is that the proportion of people with Parkinson is higher among non-smokers than among smokers. So you can write your own examples and you arrive to the conclusion that yes, this can be true indeed, right? This is known as the Simpson's paradox, where a trend appears in different groups of data, but this trend disappears or also even reverses, which is this case of this problem, when the groups are combined. So let's show this. Let's show that this is true and that this can happen, writing a Prolog program that simulates this situation. A new Prolog program. We've named this file here to be paradox.pl. You can choose whatever name you want. And let's begin this program by defining the number of people in each group. As we know from the problem statement, each group has 10 people. So we can already define here that the number of people in each group is going to be 10. We define this fact in Prolog. Right, so here let's also make a comment where we define the number of people in each group. Remember that in Prolog we can make comments with the percentage symbol. Okay, so once we have defined the number of people in each group, we also need to define the percentage of people with Parkinson's disease in each group. So in the problem statement, it is only said that in the first group, the percentage of people with Parkinson among smokers is higher than among non-smokers, and the same with the second group. So here we can basically set any percentage that we want as long as this is satisfied, right? We can choose, for instance, a value of 50% of smokers in each group have Parkinson's. We can define here the fact percentage of smokers to be a 50%. We are saying that the 50% of smokers in each group have Parkinson's. Right, so here we are defining the percentage of people with Parkinson's disease in each group. So the percentage of smokers is 50. We also define the percentage of non-smokers. Here can be any percentage less than 50. For instance, let's use 20 as an example, right? So 20% of non-smokers in each group have Parkinson's disease. We set the value 20. We also here close this fact. And here we are representing the idea that 20%, right, of the non-smokers in each group have Parkinson's disease. So now let's see that when we combine these two groups together, then this situation is the opposite. Portion of people with Parkinson's disease is higher among non-smokers than among smokers. To prove this, let's define a predicate in Prolog to calculate the total percentage of people with Parkinson's disease. Let's name this predicate to be total percentage, where the final variable is going to be here p, what we are going to have at the end. So this predicate is a rule. This is the head of the rule, and then we define the body of this rule. And so what is going to be now this total percentage? Well, first we need to get the number of people that we have in each group. So here we can just use this predicate and this fact, number of people. We access the Prolog database. So now the value 10 is going to be saved inside this variable n. We also get the percentage of smokers right here. So we just type here percentage of smokers and we save this into, for instance, P1, right? And we do the same with the non-smokers. So we get the percentage of non-smokers in each group, which is P2. What is going to be the total percentage in here? Well, this total percentage is going to be the percentage 1, right, multiplied by the number of people in each group, divided by the number of groups, added the percentage 2 multiplied by the number of people in each group, divided by the number of groups. In our case, this number of groups is 2. All this divided by the number of people in each group, right? With this, we get this proportion, this percentage. Let's define a new variable here, total. Total is going to be P1, okay, the percentage 1, multiplied with the number of people in each group, divided by the number of groups. In our case, it is 2. We have only 2 groups. Again, we can also prove that this is true with the set of groups. If we have more than 2 groups, this is also true. This Simpson's paradox is generalized to a number k of groups. Here we add the percentage 2 multiplied by the number of people in each group divided by the number of groups, which is 2, and we divide all this by n, which is here the number of people in each group. Right, so with this, what we have inside the total variable is the proportion, which is a value between 0 and 1. And if we want to get the percentage, the same way that here we have 50, 20, and so on, then we only need to multiply this by 10 and round this number as well, because maybe we also can have decimals in here. Let's also only look at the integer part of this, since it will be enough to show that this trend is reversed. So here P, which is going to be the final, right, solution, P is going to be the round of the total proportion multiplied by 800. So essentially here we have the proportion. Imagine that we have 0.62. When we multiply, we have 62%, and we also make the round if we can have decimal values, right? Imagine that here the proportion is 0.6219. Here we will have 62.90%, right? 62.19%. And with this round, this 19 is going to disappear. We are only going to stay with the 62 inside P, right? Again, this round is optional. You don't need to use the round. We are using because we don't want to work in this problem with decimal values, since this is not going to be important. Very well, so with this we have this predicate that calculates the total percentage, right? So essentially this is the database. This is the information that we send to the Prolog database. So the Prolog already knows this, right? Keep in mind that Prolog is a logic programming language. It is a logical programming language. This is information. You can say this like clauses. These are clauses, facts that we here tell Prolog, and this is a predicate. It is a rule that we define, right? So now let's define a predicate to print the results, right? So this predicate, let's just define it in here below. Let's name this to be print results. It's going to be a predicate. It is going to be a rule that what we're going to do is basically to calculate the total percentage. Let's save this into P. We can display the output, so we can do this with the format predicate in Prolog. This is a predefined predicate that, given a list of characters, given a string, which in our case is total percentage of people with Parkinson's disease, here we can insert and write the value of P as we just type here percentage W, but on Prolog with substitution instead of percentage, we need to use this tilde. So when we type tilde W, right, what we will have is a substitution that here we can specify this substitution as a list in the second argument. So this is going to be the list that only contains P, just like this. And also here we have 2 points and then the substitution. Now keep in mind that this is commonly also related to the substitution that we have in C when you use a printf instruction. However, in C we use the percentage, then the syntax, right? And then we apply the substitution. In Prolog, we don't use the percentage, we use the tilde, and also here we do this with a list. Essentially, what we do with this is to write what we have inside this element P in here, and what we have is precisely this percentage. Very well, so with this, we finish this predicate. Very important, remember to close all of your predicates with a period, a final period, right? Also here we have a period, and in the same way with the facts in Prolog. Also here, the call of the predicate total P is total P with this lowercase, right? Here we respect the same syntax on the definition. So lastly, we also add here the percentage symbol to visualize the symbol percentage in the solution. And also note here, since our facts, okay, since this proportion are already, okay, both of these proportions are already in the percentage format, we don't even need here to multiply by 100, right? Because if we had something like this, 0.5 and 0.2, we have the dimensions in a proportion format, then yes, we need to multiply by 800, but since here we are giving this as a percent already, we don't need here to multiply by 800. Okay? We only need here to compute the round, that this is also optional. In fact, you can also even type here P is this value, and you'll get the decimal percentage of the solution. We are going to round this value, so we have an integer number at the end. Again, this rounding is optional. This gives us the total, and the P is the round, okay, of this real number, right? This potential real number to a integer value. Okay, very well. So now if we run this program in the Prolog interpreter, keep in mind that we can open this file in the Prolog environment. Remember here, if we type square brackets paradox, the name of the file, we end here the square bracket and we type the enter key. If this is true, it means that we have loaded this file into the interpreter. We have loaded all of this code, right, into the Prolog interpreter. So what if we print these results? Well, this print results predicate is going to print the percentage of people, okay, in the combined group that has Parkinson's. So we press the enter key, we can see the total percentage of people with Parkinson's disease is 35%. Now, is this value 35% sufficient to prove the Simpson's paradox? The answer is no. This value alone is not enough, but it may be a red flag to further investigate the Simpson's paradox. So to demonstrate the paradox, we need to examine the percentage of people with Parkinson's disease in each group and compare them to the percentage in the combined group. So this is what we are going to do now. So now we are also going to compare the percentage and prove in Prolog if the Simpson's paradox is present in our case or this paradox is not present. First thing that we are going to do is to define the number of people in each group and also the number of people with Parkinson's disease in each group. So let's say we have 10 smokers and also 10 number of people to be non-smokers. We have a predicate number of people. Right? The first argument is if it is a smoker or not. So the number of people of smokers is 10 and the number of people that are non-smokers is also 10. Okay? So now let's define the number of people with Parkinson's disease in each group. Right? So essentially now what we are defining is atomic individuals that we have here known percentage. We are basically specifying here the proportion in the integer way. Number of people with Parkinson's disease among smokers, let's just say 3. And the number of people with Parkinson's disease, let's just say here, to be among non-smokers to be 7. Right? So here, what really is important to prove this paradox is not if this one is higher or this one is smaller. The really thing here is that here we have a proportion. In this case, this proportion is saying that we have more people to be with Parkinson's disease among non-smokers than smokers. The paradox happens when we combine them. We will find out that they will have the same proportion, or even the smokers will have a higher proportion. In the same way, if the number of people of smokers, right, that have Parkinson's disease was higher, right, when we combine, this is going to be reversed, or basically disappear. So this is the idea of this paradox. And in fact, here to even make things clearer and follow the statement and the specific situation that we are now dealing with, where the number of people with Parkinson's disease among smokers is higher, as we can see in 2 of these groups, we are going to maintain the same assumption. But keep in mind that to prove the Simpson's paradox, this is not needed. We can have the different proportion. This is the important, that when we combine, this is reversed. It can be on one way or the another way. Right? But what is important is that this is reversed. So let's just maintain the same assumption where we have more people with Parkinson's disease, right, among non-smokers or among smokers. Well, this problem statement specifies that this is among smokers. So we have a higher number of people with Parkinson's disease among smokers. So we set this value to be 7. So here we have a 70% if this is 10. And here we set this to be 3. So we have a 30%, which is smaller. So with this, we follow the same assumption as the problem statement. So now how can we prove this Simpson's paradox? Well, we're going to do this in 3 parts, okay? First of all, we're going to define a predicate to calculate the percentage of people with Parkinson's disease in each group. Then we're going to define a predicate to calculate the overall percentage of people with Parkinson's disease. And finally, very important, we need to define also predicate to compare, and this part is going to be vital in this notion of comparing. We need to define a predicate to compare the percentages of people with Parkinson's disease in each group and in the combined group. So we can make the decision if the Simpson's paradox takes place or doesn't take place. And this all is really simple. Okay, so the first thing, let's begin with defining the predicate to calculate the percentage of people with Parkinson's disease in each group. Here, let's call this predicate to be percentage, for instance. So percentage, that given a group, we're going to save this into P, the percentage of people with Parkinson's disease in this group, right? Right, so essentially let's take in this value, if it are smokers, 7 divided by 10, or 3 divided by this value 10. Right, so here, imagine if we change these values, we can also here compute very easily this percentage with this predicate. So here let's define this rule to be, first of all, we get the number of people inside this group. Okay, let's here set this to be in the variable n, where we have the number of people. Then we see here the number of people with Parkinson's disease in this same group. Let's call this PD, number of people with Parkinson's disease. And finally, we calculate P, right, which is the solution variable. We calculate P as the quotient of PD divided by n. And since we want the percentage, we multiply this by 100. We can have a percentage result at the end. Okay, with this we have the predicate to calculate the percentage of people with Parkinson's disease in each group, right? If we apply this predicate with the group of smokers, we will have 17%. And if we apply this with non-smokers, we will have a 30%, right? Okay, so now let's define a predicate to calculate the overall percentage of people with Parkinson's disease. Let's name this predicate to be overall percentage. P is going to be the solution variable. And this rule is going to have the following body. First of all, we take the number of people with smokers. So here we have the number of people, and 1 should be the number of people of the smokers group. We do the same. We access the number of people inside the non-smokers group. This is N2. We access the number of people with Parkinson's disease among smokers. This is PD1. And we also access the number of people with Parkinson's disease among the non-smokers group, right? This is PD2. Now we calculate the total amount of people. This is basically the sum. The total people here is the sum of N1 plus N2. The total number of people with Parkinson's disease is the sum of PD1 plus PD2. Finally, this final percentage is going to be this total people with Parkinson's disease, so total PD, divided by the total people, the total amount of people, both of these groups, right? All this multiplied by 100, so we get the percentage. Keep in mind that this is going to be a quotient, a proportion value from 0 to 1. When we multiply this by 100, we will get the percentage. And at the end, we end this rule, we end this predicate with this final period. Okay, so with this, we are done. Now, the last part, which is the most important one. We need to define a predicate to compare the percentages of people with Parkinson's disease in each group, also in the combined group. So we can compare this. Depending on the results of these comparisons, we will arrive to a given conclusion where the paradox is present, or another conclusion where this paradox is not present in this case. Right? So our intention is to prove that this situation can happen, right? We are going to prove this in Prolog, that this specific actuation is a real possibility in the real life. And with this configuration, where we have here, this is precisely what is happening, right? The number of people with Parkinson's disease in each group is higher among smokers than among non-smokers. But when we combine now, we are going to have a different result. So let's see this. Let's name this predicate here to compare the percentage. For instance, compare percentages. So here, compare percentages. So as we've said, we need to define here the predicate to compare the percentage of people with Parkinson's disease in each group and also in the combined group. First of all, let's take here the percentage of the people on the group of smokers, right, that have here Parkinson's disease. So here percentage of smokers P1, this is the percentage of people with Parkinson's disease in the smokers group. We also take here the value of the non-smokers group. P2 now has, inside P2 we have the percentage of people with Parkinson's disease inside the non-smokers group. We also calculate the overall percentage, right? This is P3. So this is the last function that we have defined, the last predicate that we have defined here. And so now we have P1, P2, and P3. So now we need to compare these values. First of all, merely for presentation, let's write in the terminal, first of all, the percentage of people with Parkinson's in smokers group. So here we can just write P1 in this case. P1 has this percentage value. Remember in Prolog, when we here use the predefined predicate write, we write in a line in the terminal, standard output, right? And here, if we declare another write, we are going to write in the same line. The only way to separate the lines and to add a line break is with a new line. We can see here with this NL, right? Here we are adding a new line so that the next time that we type write, this is going to be displayed in a new line. Very important, these two are going to be placed in the same line. Here we do the same thing with this write. We now write the percentage of people with Parkinson's in the no smokers group. We leave a blank space to here write the percentage. This is P2, P2. We also add an end of line, a new line here. And on this new line, we also write the overall percentage of people with Parkinson's. Here, very important, we are going to write in the same line P3. This P3 is going to be displayed in the same line as the overall percentage. Okay, so here we add a new line like this. And now, very important. The next thing that we are going to do is the most important part of this lesson, because it's where we work with the Simpson's paradox from the mathematical point of view and also the probability side. So we have the data, we have the percentages already. So the Simpson's paradox is going to take place if the trend in each group is the opposite direction of the trend in the combined group, right? Then the Simpson's paradox is present. And know that this only happens if the percentage of smokers, the percentage of people with Parkinson's disease among smokers is greater than those among non-smokers, but when we combine, this disappears. This greatness disappears. Or it could also happen the other case, right? The other situation where the Simpson's paradox will also be present, where we have a high amount of people, a high proportion among non-smokers, and when we combine, this also disappears. So let's say this. This can only happen if P1, right? For instance, the value of the percentage of people that are smokers is greater than P2. This is greater than P2. But when we make the percentage, the overall percentage, which is P3, this is greater than P2. This is one possibility where this trend is reversed, and then the other possibility is in this case when P1 is less than P2, so people among non-smokers, right, have a higher percentage of Parkinson's disease. However, when we make the overall percentage, this value P3 here is greater than the value of people with Parkinson's disease among the smokers. Essentially, remember that what this is saying is if the trend in each group is in the opposite direction of the trend in the combined group, then the Simpson's paradox is present. Remember in Prolog when we have a semicolon, okay, this semicolon inside a condition evaluation is a disjunction, also named as a OR logical operation. This is the same logical OR operation that we have on high-level programming languages and imperative programming languages. This is implemented with a semicolon in Prolog. What this is saying is, if this happens, right, or if this happens, if one of these happen, then Simpson's paradox will be present. And as a consequence of this, we are going to write that the Simpson's paradox is present. And also, we are going to add here an end of line. Now note here that we are using this backslash with this quote because here we are using a quote inside a quote notation, inside a list of characters. So here if we want to see this quote inside the text and not interpret this as a separator, we need to use this backslash, right? So here we add the end of line. And now, very important, okay? We need to also specify here, very important, the cut operator. Remember when we have the exclamation symbol in Prolog, this represents the cut operator. This means if this was true, and we have written the Simpson's paradox is present, okay, we are not going to go here below and look for the possible truth values of different predicates with the same name as this one. So this goal here, compare percentages. If this was true, we are not going to go here below. Otherwise, if this condition is false, we are not going to reach here. Keep in mind that if this is false, the rule is going to leave. We're going to leave from this rule, right? And we can go here below. And this is where we are going to define the same predicate, but now for the case where the Simpson's paradox was not present. So this is a very simple way of defining the conditional statement in logical programming language when we have the if-else case. But now the idea is that, okay, this was true. So I have written this in the terminal. This was the display. So I can have used a cut operator that basically specifies, okay, if I have reached this point in the program, I'm not going to look, okay, below in here of the same name. So all of the predicates with the same name as this are going to be discarded. We are not going to look at them. Right? We are going to just stop because this was true. However, if this condition is not satisfied, this is not going to be displayed because this is going to be false, and hence we are going to leave from this rule in Prolog, and we are going to try to find a new predicate with the same name, okay, to reach this truth value goal. So this is the case of the compare percentages in here, that we're only going to write that the Simpson's paradox is not present. So here we just write the Simpson's paradox is not present in this case, right? We also add the end of line or merely for presentation, and we end. Now keep in mind, and this is very important because it is also a review of the fundamentals of Prolog, okay, and some important notion. What is the structure of this goal here of the compare percentages? Of course, this is a predicate that is always going to be true. This is always going to be true. Why? Well, because if the Simpson's paradox is present, we are going to come here, this is going to be true, and we are going to write this. This is true, we are going to leave the program, right? Because this has the cut operator. We're going to leave backtracking process of Prolog to find new predicates with the same name. However, if this was false, and the initial result of this was false, Prolog backtracking is going to come to the next predicate with the same name, which is this one, and since on this predicate we only write a text, this is going to be always true, and we are going to leave the program. So this predicate compare percentages is always going to be true. What is important, however, is if the Simpson's paradox is present or not, and we can see this in the display of this program. Very well, so now we open the Prolog interpreter, we save this code file, we open this file, we can also verify if we are on the same directory. Right? We here just type paradox, the name of this file, between brackets, we add a final period, we press the enter key, and as we press the enter key and this returns true, this is basically saying that the file has been loaded to the Prolog interpreter, no errors have been notified, so there were no compilation errors, and this program has been loaded into the Prolog database. So now we can execute this compare percentages function that will tell us if this Simpson's paradox is taking place or not. So let's verify this. Here we just type compare percentages, right? We press the enter key also with the final period of this predicate, we press the enter key. Alright, and as we can see, okay, this is saying the percentage of people with Parkinson's in smokers group. We can also make this a bit bigger, so the percentage of people with Parkinson in smokers groups is 70%, as we have just mentioned, okay, when we define this number of people in the smokers group to be 10, and the number of Parkinson, here the number of people with Parkinson's disease to be 7, then the percentage is 70%. In the same way, the percentage of people with Parkinson's disease among the non-smokers groups is 30%, right? since we also have 10 people in the non-smokers group and 3 of them have Parkinson's, so 30% of these people. But now, what is the total average, the overall percentage of people with Parkinson's disease when we combine these two groups? We see it is a 50%. So this is showing that the percentage of people with Parkinson's disease is the same among smokers and non-smokers in the combined group. This is in contrast to the trend in each individual group, where the percentage of people with Parkinson's disease is higher among smokers than non-smokers in both groups. This demonstrates the Simpson's paradox. This is a really interesting and simple way to prove that this paradox takes place inside this problem 12, okay? And indeed, this situation can happen. Okay? In real life, this can be a case that takes place in real life. Very well, with this we end this solution of the problem 12. We remind the student that you can download both the solution as well as the statement of this problem on the downloadable documents of this lesson.